electrons have spin. Electrons do have spins. Their actual wave function has two components. Why did we regard it so far? We assumed that implicitly that scattering does not depend on spin, and indeed for potential scattering, it's most likely the case. Right, but they do have spin operator associated with electron vector Pauli matrices, three Pauli matrices, three possible directions of spin. What can be done? What factors which can make this difference pronounced or at least interesting? First of all, and I will show how simple it is in nanostructures, one could just have external spin magnetic field and make just roughly different number of electrons with different speeds. Again, either you use natural magnets or you just apply magnetic field. Right. Two ways. Either internal spin splitting or external is external magnetic field. Another possibility is to take into account spin orbit interaction. You remember simple Kirchhoff for this. Electron moves, and since it's relativistic, the electric field it feels also is a bit magnetic field, and this magnetic field contributes differently to the energies of this electron. It makes the energies spin dependent. Spin orbital direction, and okay, I eventually I could have been talking full workshop about spin effects. There are so many, so various, there are so many groups which approach this problem with very different directions. I want to give you the shortest introduction, so I won't be short. So first, Zeeman splitting, let us understand why we can have a different number of electrons. All right, so there is parabolic spectrum, and I add magnetic field which depends on spin. So the original band dash curves is split. There's a parabol going up and parabol going down. All right. So I want to fill electrons, so I put it like this. That was original chemical potential. So electrons in this band. The field up to date. Now I've got splitting. Alright, so I have different numbers of electrons. Let me give them with different colors. Spins up. Spins down. And there are much more electrons with spins down, bigger KF, but also I see a shift of chemical potential. You can explain why it has to be shifted. It's a bit of old thermodynamics, which you took at some stage. The picture is obvious. You want to regard it obvious, you skip some important details. I didn't want to change the total number of electrons. So that's why the splitting also shifts chemical potential for both species. All right? Good. Now we have just different number of electrons, different spins. So they have different velocities, different history. They behave scattered differently. Let us see simplest way to see spin effects. We can just take QPC and understand what happens to these barriers. You remember the barriers which separated open and closed antennas. That's a picture of a barrier for a certain mode. Yes, please.
Why is there no factor 1/2 in the second term? Because the splitting has to be, so now the splitting is 2G mu B, right?
If you want it here, put it here. But it's just, yeah, a factor. Right. It's important that these barriers are also split. So for spins up, the barrier is higher. For spins down, the barrier is lower. And that means that different spin species go through QPC in a different fashion. Either they are reflected or they are transmitted. Good. So here I have a curve which is similar to what I showed to you. So let me just remove experimental imperfections. So without magnetic field, it would be like this. So here no open channels, here is a single open channel for two spins. Here we have two open channels for both spin directions. If you apply magnetic field, we see that we have spin filtering. Quantization is half integer. And for instance, if I concentrate on this interval of gate voltage, only spins down eventually get through the QPC. And spins up are reflected. That's great, but it's electric current that doesn't know about spins. So in order to detect such spin current, such spin filtering, usually one needs to have a magnet or other QPC with different magnetic fields, but the effect is present. QPC is spin filter. Yes?
Why is it not
Because our conductance quantum, as we know it, is contributed by two spins. Let me remind the expression for conductance quantum. It's 2s e squared divided by 2 pi h bar. So just definition of conductance quantity. Now, if we have only one spin transmitting the QPC, its conductance is 2 times lower. Just this. Which you can see rather accurately on this experimental curve. Let me just check it for you. So this is first quantization, this is half integer quantization. It goes very neatly. So I guess even Sergei Frolov would have been satisfied with the reproducibility of this experiment. Good. Let us try to recall spin-orbit interaction. Okay. First of all, as I said, it's relativistic effect. This is a Hamiltonian. It contains electric field. It contains velocity. And it contains spin. All go together, and there is a relativistic factor reminding about that effect. Since the velocities of electrons are very small as compared to velocities of light, generally one can estimate scattering time proportional to squares of Hamiltonian, and compare it with the spin flip time. Well, there is a vector of a ratio of velocities. That appears to be material dependent, and the reason for that is that in heavy metals, electrons are closer to nucleus and they are go faster. So for heavy metals, spin flip scattering can be quite big. But for many, it just nescence, and the electron, which goes through metal and scatters, has to experience like 10 to the 4, 10 to the 5 scattered events before finally it flips the spin as well. Right. Which means that spin can exist at long distances. Distances which are required for electron to travel before it experiences spin flip event. Right, let us have some philology, but let us write down scattering matrix with spin indices. So I took it in channel space. Now I add spin indices. There are scattering processes without change in spins, scattering processes with change in spin. Well, I can see it generally as something which comes with a vector of Pauli matrices. Let me look at the spin-dependent part. Let me formulate general rules for that. Time reversibility, which is the case of spin-orbit interaction, implies that this matrix is anti-symmetric with respect to change of indices. While for magnetic part, it is symmetric. Does it go through? Fine. Right. That property eventually implies that we cannot arrange, for instance, spin filter in one channel conductor. For one channel conductor, even if the strong spin-orbit interaction, there is no part of the scattering with a change of spin. Right. we've been talking about electric currents, see, I've forgotten what I have with this. All right, I really hate attempts to make animation with PowerPoint slides, but I guess it was an attempt. But yeah, it's good to do it like this. Let us first define spin current from the point of view of general physics, operator of spin currents. So we have some particle with velocity and a spin in certain direction is carried. So spin current eventually has two indices. One index is the direction of the current, another index is the direction of spin. We could easily measure measure electric currents. How about spin currents? That's interesting question, and conservation is taken practically. Generally, spin is not conserved. Spin flips in the course of electron scattering. So then it's not concerning, then we cannot measure it as easily as electric current. However, as I said, this non-conservation of spin happens at large distances. That's why we have some room to observe these spin currents. We need to look at sufficiently small distances, consider spacing, which are smaller than the spin flip lengths. All right. That is what I said. It's about non-magnetic metal. If I look at ferromagnetic metal, then this kind of conservation is somehow a little bit more complicated. We take ferromagnetic metal where all the magnetization axis is along Z. Then numbers of electrons you spin up and spin down would be conserved. Again, if I don't think about flipping that. But what happens to two other components of the spin? They will be killed very fast. Why is it so? Because spins of different directions have very different history. They move with different velocities, they experience scattering differently. And what is spin in x direction? This is a superposition, quantum superposition of the states with spin up and spin down. So if components of superposition will differ in their history, the effect of superposition will be erased very soon. Good. Practically, there are two possibilities for this slow non-conservation. In non-ferromagnetic metals, all spin components are supposed to be conserved some distance. In ferromagnetic metals, only single component can be conserved at sizable distances. Right. Again, let's try to repeat what we already did for the quantum point contact. Let us apply voltage to nanostructure. We can get spin current. It's encoded in properties of scattering matrix. Another question: how to detect it? Right. In most, there's no spin current ampere meter. Unfortunately, nobody has invented it. But fortunately, there is spin voltmeter. So how come? What happens? If you just send spin current to some place where electrons can be accumulated, different numbers of spin will be accumulated. There will be different chemical potentials for different spin. And that can be measured. How? Let's take another spin filter. We could realize it with the QPC, or we can, usually in practice, it's realized with ferromagnetic metal as interface. So the electric current of this extra interface will depend on spin accumulation. Right. So if you want to make kind of electric theory for spin currents, what do we need? We need spin currents and also spin voltages, accumulations related to different components. Accumulation, here I was talking about accumulation in that direction. Eventually it can be in any direction. Right, and let me just try to talk about spin scattering in very simple and classical way, which appears to be very instructive because there's an amount of people who can understand these concepts. It's much bigger than number of people who do not want to understand quantum physics. Yeah, there is. It's interesting how does it change into dimensions. When I was a student, all this science about lasers, optical beams, has been called quantum electronics. Actually, I don't think anybody of you ever heard of this. But we had, for instance, faculty department of quantum electronics. Then laser field expanded and became more applied, and we really needed engineers to get on these lasers rather than physicists. That gave rise to a series of books who stressed even in title, you don't need quantum mechanics to understand the laser. Please buy the book, everything will be fine. And quantum electronics has disappeared within years. Just by practical demand. So let's try to make this theory of spin currents as simple as possible. First of all, let us make it for two spin directions, considering it as two separate species. If there is no spin flip, that will work. What we get? We get current of particles with spin through interface. Okay, that comes with transmission coefficient, specific for the spin direction. Right. Now I can sort it out. I can get electric current. And this current will be proportional to voltage and also proportional to spin accumulation. There's a way to detect the effect of spin. Right? Or I could also think of spin current. There will be spin current proportional to voltage applied and a path proportional to spin accumulation. Good. That means that is ultimately simple. If Nobel Prize was upon my influence, I would never give Nobel Prize for these things. Other people did give it. It was a theory of spin filter. Right. Let me mention a thing which is manifestation of quantum effects. One can try to evaluate situations when spins don't have to be directed, they don't have to be quantized along the same axis. One can try to derive these equations for arbitrary spin direction. What one would get? Okay, so what I want to hear, I want to do here, spin current in x direction, perpendicular to quantization axis in the y direction, and I want to relate it to accumulations in x direction and y direction. So in principle I need 2 by 2 matrix, but okay, owing to spin symmetry, there's only one complex number which characterizes this matrix. And that funny property, funny coefficient, is called mixing conductance. Okay, one needed quantum physics to discover it, but again, you can boil this down to engineer levels. Right, so there are also currents in perpendicular directions. What I want to mention that this mixing conductance is naturally expressed in terms of Landau machinery. In this case, one has to remember that there are 2 scattering matrices, 2 reflection coefficients for 2 different spins. Right? So it is arranged in this way. If there were 2 same spins, for instance, spin up here and spin down here, it would just give us the sum of transmission coefficients for spins up. If both spins are down, it will give us the same. But there's yet another kinetic coefficient in spin current propagation, which also obeys Landau formula, but with a twist. Spin mixing conductance. Why it's mixing? Because it mixes the spins as you see. I think I'm done. Let me just check it. Yeah, that was it about spin. Right, so what I did, I just bring spin dependence to scattering matrix and was trying to outline simple effects related to this dependence. Shall we make another break, or I could just start with first lecture if you don't feel tired. So let us see. Let me find the next lecture. when I was a student, we got very different courses, but my teachers were persistent in saying, it's a single science, single course, please don't separate your knowledge into separate boxes in your mind. It all has to go to single part. All right, that worked, and I'm trying to do the same now. I try to get to the same box what I told about quantum transfer and what you have heard perhaps here at school about Ohm's law. First of all, I tried to find to confirm technical things that theory of scattering, which we have looked at, does not contradict the Ohm's law, eventually reproduces Ohm's law. The difficulty is that you immediately hit paradoxes, well, which can be solved, but no, there's something to talk about this. And the concept of averaging and self-averaging will be important here. Then, I guess Professor Ostrovsky will tell you more about this, but I also, again, remember that I do it for master students, and I would like to just give most important block information, we can go to the details. Then I want you to get into time machine and understand how people treat electron transport in solids just about 100 years ago. We will understand how clever people were at the time. If you wish, it's a theory of classical quantum transport. I will end up with Kirchhoff circuits with finite element approach to electricity. After that, I could skip this part, but if time allows, I would tell you that Kirchhoff theory is eventually based on the balance. And I give simple examples of using balance in quantum transfer. But that doesn't stop me. I will tell you very strange thing. I will tell you that quantum mechanics supports more and much more conservation laws that you can find in classical mechanics. That sounds pretty heretic, because we have learned that quantum mechanics should just be consistent with classical mechanics, just minor extension. But it's not so, and I will discuss it at some stage. We will find more conserving currents. We will look at some examples. And then what I want to do is to make Kirchhoff kind theory for all these extra quantum mechanical currents, which is called quantum circuit theory. I wouldn't have time to go through examples. I'd have Professor Ostrovsky would do it, perhaps at a bit more formal level. Right. But I want to say several words about this, and most importantly, let me tell it in very beginning, before I've forgotten it by the end of the lecture. Quantum circuit theory in case I describe is a template. There are some general rules which can be formulated with almost no regard for a concrete physical system in mind. You could say that that doesn't make sense. Let us understand that classical conservation laws also can be frequently applied in terms of templates. One can think of conservation of particles, or conservation of heat, conservation of energy, and all these equations eventually very similar. Third, that shows that the language of templates is also useful in physics. All right, that is a problem. Let's see how far we can get before you're completely exhausted. First of all, making bridges. We want to connect one side of quantum transport, where we talk about electron waves, about scattering matrix, to another side, to classical electron transport, when we talk about electric currents, Ohm's law, circuit elements, these fine diagrams have to be connected somehow, and simple bridge just to show that Ohm's law, classical transport, circuit theory, after all, follow from quantum mechanics. And then the golden bridge, that's what I mentioned, one can use extra conservation laws applied by quantum mechanics to investigate quantum mechanical structures in what this means. Fine. So let me start with paradox, which almost as silly as Russian riddle I mentioned to you. Double junction paradox. Eventually, it should be no paradox for us because yesterday we have seen exact formulas explaining it. But still, I want to take two double junctions in series. That means that probabilities to transfer are very simple, small. Tunnel amplitudes are very small. Good. I want to understand the transmission coefficient. I need to multiply amplitudes. So I get something much smaller. Amplitudes are related to conductances, so I don't do exact calculation, just estimate. Right, so the total conductance of double barrier would be proportional to the product of two conductances. I have to keep dimension right, so I just divide it by conductance quantum. Good. That's what quantum mechanics tells us. Right? It's just based on the fact that amplitudes must be multiplied. Let's recall what Ohm's law tells us. In that case, you just add resistances of two scatterers, and to get conductance, we get this. And you see there are similarities and differences. Similarity is this factor, product of conductances, here and here. But denominator is completely different. Let's check the scaling. If one changes conductances of two junctions by a factor of 2, what is the change expected in this case? Conduct? Follow me. So G1 is increased by a factor of 2. G2 is increased by a factor of 2. The total conductance is a product of the two. No, I'm talking about this formula. So, 4 here, and 2 if we use Ohm's law. Fine. Right, so how to solve it? The solution is known to us because we have already solved two-barrier problem in all its glory, taking into account phase factor in the spacer between conductors. That's the formula which we obtain. It contains this phase factor. Let us now average it over all possible phase factors to start with. I don't remember if I mentioned this. This is equivalent to summing up of probabilities instead of summing up amplitudes. Did I tell you that? Actually, I don't recall. But okay, yeah. Perhaps you were able to get it yourself. Right. So after this, we got, wow, at low transmission coefficients, we got almost what we want. If I consider small transmission coefficients, it will look almost like Ohm's law. Yeah, let's look in more detail. I wonder if you can see the details. Right. I plot the transmission versus phase, which comes here, or versus energy. So I have a series of peaks. You remember Fabry-Perot pattern. And at the peak, transmission is about 1. In the minimum, and peaks are narrow, so this minimum eventually gives you typical transmission. At the minimum, it is t squared. So eventually, my initial estimation was not so stupid at all. However, if I look at the average, this line, it is in between. It is much bigger than bottoms, it's much lower than peaks. Average transmission is proportional to G. It gives us an idea how to come to Ohm's law, but we are not there yet. Let's do it in some steps. First of all, let me consider many channels. I wonder if you could see that. Here I plotted in different colors the same series of peaks of resonant peaks. They're not periodic because the periodicity is different for different channels. Then I sum up the conductance, that's what I get. It's already pretty at average level, it fluctuates still, but that's because I just only took 6 channels. Yeah. Okay, let me derive a transmission for this case. In this case, I just do it for each channel separately. Each channel will contribute this average, but it's not quite the same as Ohm's law. But we are on a good route. Now we need to mix the channels. In addition to averaging within each channel, we also mix one. Right. And this is true representation of Ohm's law in scattering transfer. We have two conductors, two connectors with transmission coefficients T1 and T2. But the space between, which was just a phase vector or single channel, becomes a full-fledged scattering matrix with as many channels as we find in this conductor. And now, if we average over all realizations of the scattering matrix, we are finally back to Ohm's law. That's how it goes. I wish it were simpler, but that's how it goes. It's how the Ohm's law is reproduced in quantum mechanics. I shall say that in contrary to what you sometimes hear in popular outline, it has nothing to do with the equilibration of electrons or with losing quantum mechanical phase by those electrons. Here in these setups, electrons are quantum waves. Nevertheless, Ohm's law is restored. Right? Let me talk a little bit more, some philosophy about these phase shifts. You need to read this first. First of all, let me remind that any unitary matrix is just a set of phase shifts. How do we know this? Mathematically, we diagonalize unitary matrix, and eigenvalues of any unitary matrix are just phase shifts, complex numbers of modulus 1. All right? Yeah, if you look at it physically, if the structure, if non-structure is bigger than phase length of electrons, there's a chance for a big phase shift. And also there's a chance to affect this phase shift, for instance, by disorder, by fabrication errors. So, at least at present day technology, when we cannot really shape world atom by atom, it will be fair to say that we cannot control phase shifts, at least at fabrication stage. So there's an attempt to make identical nanostructures with design phase shifts, but okay, in practice scattering is affected by disorder, which is inevitable, fabrication errors, and even if one if one really washes hands carefully, one gets rid of disorder in the leads, one can get rid of fabrication errors. In the leads, there's still disorder. One cannot really purify a lead which is 1 meter long. Good. So it's fair to say that we cannot control phase shifts and perhaps won't control them for a very, very long time. And if we think that we make identical samples, we don't make identical samples. Right. It would be perhaps good to have one-channel samples, and with gate electrodes we can tune the structure to whatever we want. But that could not be possible for more channels. Number of parameters to control grows as n squared with the number of channels. So it's like, in general, we cannot know all phase shifts. Randomness of the nanostructures is our ignorance. But fortunately, our world is made by laws of mercy, and we don't have to know everything to survive. Perhaps we don't have to know all this number of parameters, And complete mess, complete ignorance can be very simple to understand, like, for instance, statistical physics is an example. There is a zillion of molecules in this room, and each has a position and velocity. Suppose that you want to, suppose the situation is that you need to know everything to control a condition. Okay, that will make you crazy in a nanosecond. What we need to know is just a few parameters: pressure, oxygen level, temperature. That will be enough. So, like in statistical mechanics, we need to talk about everything which will lead us to classical transport. From the kind of methodological point of view, it would be averaging over formally identical samples. But that would never be that's impossible. And those students spent 3 years in clean room just to make a single working sample. So in order to have averaging over 100 times, over 100 samples, one would have to extend PhD term to 300 years. Which is, eventually I would enjoy this, but it's not practical. Good, so one can only hope that the averaging will take place instead of the same sample, self-averaging, just because the conductance is contributed by many channels. In this case, we will restore Ohm's law. But as I said, there's still some quantum mechanics left because we restore Ohm's law, not by traditional elastic processes, not killing quantum superpositions. We still have waves, quantum waves living on our sample. There's still some quantum mechanics left at the stage when Ohm's law is perfectly restored. Right, time machine. We go 100 years ago. People understood that electron transport in solids is eventually very complex and very, I would say, hopelessly complex. Right. They knew Bloch waves. They understood that eigenfunctions of electrons in crystalline solid are perfect, are very similar to plane waves. But the transport is scattering also in bulk samples, so one has to consider scattering on impurities in this crystal lattice, which kills periodicity immediately. So each impurity gives rise to scattered wave, and the wave pattern, which was so simple for plane wave, just a sequence of lines, already for 3 impurities become hopelessly complex. Now we take a sample with zillion atoms, with zillion impurities. Quantum mechanics collapses here. Fortunately, people were clever by that time. They have also a little bit duality in brain, and they understand, okay, go down this quantum mechanics. We can just treat electrons as small ball of yellow color, which goes through the sample and is scattered, the particle, from time to time. Good. Next transparency is an attempt to make it mathematical. Just flash most important equations in classical notation. Let me start with useful quantity from the point of view of classical transferred. Filling factor, which depends on momentum and on coordinate. Something which we have heard about in the first slides of the first lecture. Right. In principle, if one works hard, one can fetch a quantum mechanical expression for this filling factor, for distribution of electrons in momentum and coordinate space. That will contain all exact eigenfunctions and Bezotter potential. And what I have to do here, it's called Wigner transform. When I go from a quantity which depends on two coordinates to a quantity which depends on coordinate and momentum. Just do Fourier transform over difference of coordinates here. Ooh, that could have been a starting point, but okay. Fortunately, 100 years ago, people did not take it as a starting point. They could think in much simpler terms. What we just need is conservation of number of particles. So if we take a box that's supposed to be six-dimensional drawing, right? I'm in six-dimensional space, three components of momentum, three coordinates. The number of particles in this box would not change with time. Conservation of particles. However, this box also moves in time, right? How does it move? The time derivative of coordinate is velocity, time derivative of momentum is a force acting on the particle in this particular point. That's why we write it in partial derivatives. So now we have an equation to solve for filling factor, for number of particles, which depends on coordinate and momentum. That's called Liouville equation. Right. And that gives moment to bring impurities in. We would consider them as scattering events, right? So we have a picture of scattering where electron with momentum pi prime is scattered to the state with momentum pi, and the electrons from the state with momentum pi are also scattered in all other directions. So these two terms in balance equation, master equation, which is in this context is called Boltzmann equation, they are grouped in this way. Each scattering gives rise to positive terms, which show income, what comes from other states, and with negative sign, those are terms of expense, what goes from given state to all other states. Right, so Boltzmann equation is for bookkeepers, but okay, it's a fine equation to work with. Good, where we are now, we are at the stage of Boltzmann equation, and okay, our drive is to make it simpler and simpler and simpler. After all, we want to sell it to engineers. Still, there's a long road to this. So, what are the steps? First of all, let's consider space scales which are bigger than the mean free path. What's mean free path? electron goes through a metal, sooner or later it gets scattered, it changes its momentum by effect of time. Right? That gives you certain length proportional to impurity, inversely proportional to impurity concentration. If you look at the scales larger than that length, then distribution is isotropic or almost isotropic. Why is it so? Because at the scale electrons have been scattered many, many times, distribution must be isotropic at the scale. Fine. So what we can do now, we can, I'm still talking about elastic scattering, so there are particles at a given energy, but they diffuse. Let me write diffusion equation. I think it would be most complex diffusion equation in your life, but the intention to make it simple. I make it into equations. First equation is just conservation of particles. Change of field vector at a given point is the divergence of a certain current. What is a current? It has two terms. First term is called drift. This is how current is driven by external force. Second term is diffusion. So what we got is called drift diffusion equation. Right. What is to pay attention for? This letter D comes in both terms. Who knows why? Who knows how to prove this? One does have to be Einstein to figure it out. Although, eventually it was Einstein who first came to this idea. To check this, one should understand that in the state of thermal equilibrium, there should be no current. And what comes from potential force, drift, should be exactly compensated by diffusion. That's why the coefficients are different. And this is Einstein's relation for mobility. Mobility is a reaction of particle on the force. Diffusion is how quickly does it diffuse. Right, good, we are almost there. We just need to integrate it over energies. So the energy of particles at given, the current of particles at given energy will become full electric current, and that will become full density. And the current will have drift path proportional to electric field, right? And it will have diffusion path. So sorry for checking your electrostatic basis. How we can simplify these equations even further? We are talking about metal now.
Constant.
Say it again?
Rho is constant.
Yeah, rho is constant, so we can neglect all derivatives of rho's, and we have current, which is proportional to electric field. Great, result of quantum transfer. Fine, now let us recognize that this is still differential equation for classical transport. Current is indeed proportional to local electric field, that's right, but the current must be conserved. So that will rise to equation for distribution of voltage. So now we have a practical problem. Suppose we have two metallic leads of this shape coming together, and we want to understand how current is distributed between three leads if voltages are applied. It's clear what to do. We just take this equation and put it into computer. It will work, chop, 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 chop. In a couple of days, you'll have the solution. That's good, but in order to develop this computer or even electric bubble, which we have, one needs to solve this equation. So H22, there is no way around. Good. That is, in my mind, the greatness of Gustav Kirchhoff, who told us you don't have to do this at all. Instead of trying to really take into account every detail of the shape of these conductors, we could just replace it by some elements, and then the solution of these equations, differential equations, will become very trivial. Let me remind Kirchhoff's theory, because I will need it in some time. In Kirchhoff's theory, there are nodes between some connectors and the leads. So for this circuit, we have only one node, but three leads. In each connector, we define the relation between voltages and currents, which is so simple for linear system. And then we use Kirchhoff rule, which is just, without naming it, just conservation law. Conservation law of currents. Sum of all currents for every node should be zero. Good. I don't want to solve it as a blackbird, because everybody can do this. Right, let me perhaps skip what I want, just flash it. What I wanted to show now, how to apply balanced equations, Kirchhoff type, for different situations of quantum transport. That was for elastic transport. That was for situation where inelastic processes have occurred and the electrons in spacer are thermalized. Two parameters of the state: chemical potential and temperature. Two equations to solve: balance of electric currents, balance of heat flows. Another example how balances would work. Right. Again, a little bit of philosophy here. Coherence. What does it mean? It means that the phase of wave functions, phase of scattered waves is kept. Station disorder conserves this coherence. So, if electrons scatter in complex structure, whatever channels there are, they remain coherent quantum waves. Station disorder conceals the coherence. Why? Because if we measure the same circuit, we just restore Ohm's law, we restore all the classical answers. Right. There are ways, experimental ways to check whether this conductor, which obeys Ohm's law, stays quantum coherent. One could look at noise, one could look at traces of interference. That's what we see, Charvin experiment, universal conductance applications. One can use superconductors, magic mirrors. Right, that all works for station disorder. Non-station disorder basically would kill quantum mechanical phase. Right, let's see, I'm completely lost with respect to time.
The lecture should end at 5:30.
5. Let's see. We can still afford a 5-minute break. I could go, I'm in a state where I would not pay attention to any breaks, but how about you? Who wants 5-7 minutes break?
Yes.
Good, majority.
Ale